Hi there. In this video, we will see what are oracles in quantum computing, and then we will also check out how to create oracle using Classiq SDK. So first thing is, what is oracle? Oracle we can think as a magical black box which we are not aware what is its internal implementation or what is its internal structure, but we know that if we pass or ask some question it will always give us correct answer. So that thing or that device we can think as oracle, and we can represent oracle in quantum computing like this. This might look weird if you are looking this first time, but don't worry, we will see why it's like this. First, let's see what are its characteristics. So this is u of f, and its oracle, and it takes two input: primary qubit, which is denoted by x, and it also takes helper or ancillary qubit, which we are denoting by y. And in output side, if we see, we get input x as it is. Now it might look weird that we are feeding the input and we are getting input as it is, but yeah, we will get this input in output as it is, and here we will get XOR of this qubit by and the function fx which is inside this oracle. So here we will get y XOR fx. Now let's see why this oracle looks like this. So to understand this, we need to go back to the basics. So in classical computing, in Boolean algebra, all gates can be implemented, or all gates can be constructed using NAND gate. That's why it's also known as universal gate. And NAND gate is made up of two components, NOT gate and AND gate. Now if we see NOT gate, clearly it's reversible in nature. If we know the output, we can predict the input. But in case of AND gate, it's not reversible in nature, because for single output there are multiple inputs. But according to laws of quantum mechanics, all quantum operations and hence all quantum gates must be reversible in nature. That's why we can't use this AND gate to prepare quantum gates. Now we need to find out some alternative of AND gate. So control swap gate seems to be good alternative of AND gate, and how it works is that it takes three inputs and it spits out three output, and if it works like if this a which is target here, if it is 0 then output comes out as it is, but if control is 1 then these two are swapped, means in place of b we will get c, and in place of c we will get b. So that's how it works. Now if we hard code that third one as 0 like this, then we get functionality of AND gate here. We will see the truth table for more clarity. So we have a, b and c. C we will put as 0, and these are all possible combination of a and b. Now for first these two rows we will get output as it is. Reason that this control is 0 and hence nothing will happen. Now in the third row we have control as 1, but these two are 0 0, so nothing nothing visible thing will happen here, so we will get this thing as it is. Now in the last row we have a as 1 and b and c as 1 0. So in output these things will be reversed as 1 0 will be reversed as 0 1, and for clarity this is 0 O1 O2 O3 means output 1 output 2 and output 3. And now if we analyze the outputs, we can clearly see that the A came out as it is in this output 1, and in output 3 we are getting AND of A and B, means for these 3 row 0 and for 1 1 we are getting 1. Now we have NOT gate and we have C swap gate, and we can use these two gates to construct any gate. And benefit here is that since C swap is reversible and not gate is reversible, this means whatever gate we will make using these two, that gate also will be reversible in nature, and hence it can be used in quantum mechanics or to construct the quantum circuit. Now, since we are using C swap here, means in C swap we saw that here we have junk here. So if we construct a circuit using C swap gate, then we will get output as x, which will be actual input, and then we will get f of x, whatever function we want to implement or whatever gate we want to implement. Here we had implemented AND gate, but here whatever gate we want to implement, that we will get. And then since here we have junk, we will not get rid of this junk, and junk will appear here also, whatever quantum circuit we will make out of these two. But problem here is that this junk might interfere with the output and disturb the result. So what we can do is that since we know that this circuit is reversible, we will again feed the output to the gate again, and we will get whatever input we had here. So now you might think that we feeded something, we got output, and again we feeded it to the reverse of this gate, and again we have input. So everything is lost input, and means you feeded input and you also got input. But what we can do here is that we can take one auxiliary or ancillary qubit or bit. We can take it, and here in the intermediate step we can do the XOR of f of x and the ancillary qubit which we had taken. So it will look something like this, and if we see, then we can represent it like this. So we have x, y, and 0, and then in output side we got x and XOR of f of x and y, and then 0. What here we can do is that we can ignore these two zeros, so it will look like this, and that's how we arrived at this circuit. So in short, if we want to summarize why it looks like this, we can say that it's because of reversible nature of quantum circuits. We are doing all these mathematical manipulation to fit it into that criteria. So this is what oracle is, and we saw why it looks like this. And now let's use Classiq SDK and actually create one quantum circuit to better understand it. So from Classiq I will import these things to create the circuit, and from built-in functions I will import state preparation and arithmetic function. And what we are going to make here is that we are going to make arithmetic oracle, means here we will feed the input to the oracle, and then we have some query, and this oracle will tell if our inputs satisfy our query. So I will run this cell, and I am feeding two single bit qubits, and first qubit is in state of 0 and second qubit is in state of 1. So here I am passing probability, and then using state preparation function, this state preparation function will handle in while creation of circuit, it will handle what gates to attach to get this probability. So I will just run it, and then we have this arithmetic function. Here we need to pass the expression, what expression we want this arithmetic oracle to evaluate, and then we need to pass that definition of registers, and then we will run it. So it will open in separate tab. We can also execute the circuit here, but to analyze it, we are opening it in the separate web IDE, and here it is. So here if we see, we have these two inputs A and B. If I open it and expand it, we can see that Q0 which we passed, Q0 was in 0. So yeah, it's 0 here, and here NOT gate is applied to make it 1, and then it's passed to this arithmetic oracle, and here we will get the result. If our inputs are evaluated true, then we will get 1 in the result. If these are evaluated as false, then we will get 0 in the result. Since our input is 0 and 1, so its sum will be 1, and this is true, so we will get 1 in the output. Let's execute it. So yeah, we got 1 here. Now let's go back to the circuit and expand this oracle to see what it have. So we can see whatever we saw there in theory part, we can see we have this adder circuit here, and then we have reverse it. We are reversing, we are passing the input, then we are getting some output through this adder, and then we are again passing that output to the adder, and this is the auxiliary qubit which is XORed with you see it's a pretty big circuit. So this is XORed with the intermediate steps, and that's how it's able to get the final value for us at the end. And this is here the beauty of Classiq. You just need to pass the expression, and everything is handled by Classiq synthesis engine. Suppose I will again modify it with, suppose I do a minus b equals 1, and again let's run these two cells, and yeah, it open a new tab. So if we see here, this time we got subtractor circuit instead of adder circuit. This one was adder circuit, which was looking like this, many gates there, and this is for subtractor. So here we just need to take care of our expression, or in word sense, if we say, we just need to take care of our algorithm or logic. Everything at the gate level implementation, it's taken care by Classiq synthesis engine, and yeah, then we can execute it and see the output. So let's see output for this one also. So what is expression? Expression is a minus b equals 1. I guess a is 0 and b is 1, so output is -1. Let's see what it evaluates. Yeah, we got 0 because output is -1, and we are saying is it equal to 1, and since it's not equal, that's why we got 0 in the result. So now these are observations which we saw, and now it's time to complete the tasks. So I'm expecting that you have to go through these two tasks and then complete them, or try to complete them, and then after that you can come back and continue from here. So let's see what we have in task 1. So in task 1 we are given this expression, and we need to complete this code to evaluate this expression so that it executes to true. So I will just do for the first one. So our expression is a plus b equals 0. It's I pasted just expression as it is here, and make sure that expression is pasted as string, and we also need to prepare the state. We need to pass the probability. So it says since a plus b equals 0, so we can do many things. We can make a equals 0, b equals 0. We can make a equals 1, b equals 1. That we can do. Then there is only one option. We can make both sides 0. Yeah, my bad. We can't do anything else. So I will make 0, 0. And 0 plus 0 is 0. So yeah, now it should evaluate to true. So here we have the circuit, similar one which we saw for last circuit which we created, and then I will run it. Yeah, we got output as 1, means this expression is true for these two states. Now second one is a minus b equals 0. For this we can do multiple things. I think first thing, I can leave it as 0 0, which will be a minus b as 0. Second thing I can do as 1 1, means 1 minus 1 equals 0. So yeah, two probabilities for this one. Both answers will be correct. And third one is a plus b equals 2. So now I think it's straightforward. If both input are 1, then output will be 2. You have to just update it for 1 1, means it will become 0 1. Here also it will become 0 1, and update the expression and run it. It should output 1. Now let's move on to the task number 2. Here we have to modify the code to so that this expression evaluates to true. Now if I see the code here, expression is already pasted, which is a plus b equals 2. Second thing which I need to see is the size of registers. We see the size of registers is 3, means there will be 2 to power 3 base states, means we need to put the probability of total 8 states here, means 2 power 3 states. So for each qubit we need to pass 8 states. So for first one, let's make it as 0, or let's make it 1, or let's make it 2. So 0 0, and then 0 0, and then 0 0 0 0. So total we have probability of 8 states, and it's like first one will be for 0 0 0, this will be for 0 0 1, and then this will be for 0 1 0, and this will be for 1, I mean it will be for 0 1 1. Yeah, similarly it will go till 1 1 1. So this one will evaluate to 2. Now for b I will pass all 8 probabilities, and for 1 1 1 I will make 1. So now we first qubit is in it's equal to this one, means I think it's 0 1 0, and this one is 1 1 1, means 7 and 2, and 7 plus 2 equals 9. So it will work. Alternatively, here I had done 7 2, we can do 6 3 5 4 also. That you can try. I will just run it. Okay, in the error we got probabilities must be length of 2, must be of power 2. Okay, let's see. 1 2 3 4 5 6 7 8 9. Okay, here I passed 9. We need to pass 8 probabilities. Okay, we got the circuit, and we can see that we have Q0 to Q2 for A, Q3 to Q5 for B, and Q6 and Q7 are auxiliary qubits. Now, here similar pattern we see, we have adder and then we have adder again to reverse the circuit, and here if we see we have MCX. If I expand down further, then somewhere it should be doing that XOR operation. Yeah, it's doing here. It's doing here only, these places. And now I will execute it and run the circuit. So yeah, output is coming as ones, means our states are satisfying this expression. You can modify and play it for 5, 4 and 6, 3 also. So this is it for oracles. Thanks.